Good morning or good evening, good afternoon, good night, wherever you're joining us from. I'd like to welcome everyone to the 8th webinar of the WCRP Digital Earth's Lighthouse Activity webinar series. My name is Rosimar Rios-Berrios, and I'm from the US NSF National Center for Atmospheric Research in Boulder, Colorado. And I'll be one of the moderators of today's event. The webinar series is part of WCRP Digital Earth's Lighthouse Activity. The aim of this series is to help maintain more regular and open dialogue between active researchers and users on the development and evaluation of kilometer-scale global and large domain models across the world. We plan to hold these webinars every 2 months, spanning a range of groups working on kilometer-scale modeling around the world. And you can find a recording of the previous events via our webinar page, which we will put shortly on the chat. The focus of today is on introducing the WCRP Digital Earth Global Hackathon to support international coordination and collaboration to explore the value of kilometer-scale global models. Before we get started, I would pass it on to our other moderator of today, Huw Lewis.
Hi, and a warm welcome to everyone from my side. So I'm Huw Lewis from the Met Office in the UK. And just before we go on to introduce our speakers, to provide an overview of how today's events will run and the modes for interaction. So shortly we'll be handing on to our 2 speakers who will provide a talk, and we'll close out the session with a Q&A. So as the talk is progressing, you should be able to find a Q&A box at the bottom of the Zoom window. And so please feel free to lodge any questions you've got as we go through in that window. You can hopefully find a thumbs up voting button so we can prioritize the questions that are getting the most interest as we go through. I'd ask if you can please just reserve the chat function here for any technical issues you may get through the webinar. And again, a reminder to therefore use the Q&A for questions as we go through. After the talk, Rosie and I will then work through our questions in as much time as we've got available, and we'll try and get through everything. For presenters, we'll give you a little warning if we find that we're drifting on too long in the session, but I'm sure we'll be keeping well to time. And again, a reminder that we're currently recording this event, and we will share the recording after the event when it's available on the WCRP website in the coming weeks.
Today's webinar will introduce the Digital Earth Hackathon, as I mentioned before, to be presented by the co-chairs of the Digital Earth Lighthouse Activity. We're very happy and honored that they are able to join us today. So first off, we have Andrew Gettleman, who is based at the Pacific Northwest National Lab in the US. Andrew is a scientist specializing in clouds and climate change. His work concerns the development and analysis of global model simulations of the climate system, with a focus on the development of physical parameterization of clouds in global climate models and the physics and chemistry of the upper troposphere and lower troposphere. In addition to developing and managing our system models, Gettleman is involved in model evaluation, data analysis with satellites and field programs, and has served on science teams for both satellite and field projects. Andrew started at the PNNL, or Pacific Northwest National Laboratory, after being a senior scientist at the NSF National Center for Atmospheric Research for many, many years. Our second speaker is Pierluigi Vidal, who is based at the University of Reading in the UK, where he is a professor of climate system science at the university and senior scientist at the Climate Directorate for the UK's National Centre for Atmospheric Science, or NCAR. His research interests are focused on high-resolution global climate modeling. Professor Vidal is director of a new 15-year program called Advancing the Frontiers of Earth System Prediction, which is a broader partnership between the University of Reading with ECMWF, the UK Met Office, and NCAS. With that, we welcome both Andrew and Pierluigi to lead the presentation. The floor is yours.
Thanks, Rosie. Okay, Pierluigi, you want to start?
Yeah. Thank you, Andrew.
Just let me know when you do advance the slides.
So this is a major activity in our lighthouse in that we are starting to do something very practical, which is launching this hackathon this May, and we'll tell you a little bit more during the talk. But I'll start off with a bit of motivation and capability. Can I have the next slide? Thanks. So for a while, a number of groups have been developing models at sub 10 kilometers, and some groups have focused on developing models that are non-hydrostatic, but these are global coupled models that range from 10 all the way to 1 kilometers, and some people have ventured into simulating entire years or number of years. And we have examples on this slide of some simulations from Japan on the bottom left. So we have a comparison of precipitation from one of the observational products and one of the NICAM simulations, showing you the distribution of precipitation and also a zonal mean. And this plot, which is in the recent Taksuka et al. Paper, is one of the main motivations for the hackathon. And you could notice, and Andrew very quickly noticed this plot early on, that the WITCZ typical error is absent from this plot. And this has repercussions actually for coupled models. And Rob Wills has a whole theory on what this does to the rest of the climate system. Then on the top right, we have capabilities from China. So we have also a coupled model with a 3-kilometer ocean and 5-kilometer atmosphere, and it's run also for multi-year. We have a plot of very, very interesting and important structures in the ocean near Japan. And then in the bottom right, the other components of the climate system. So the cryosphere aspects of the cryosphere are also simulated at these sub 10 kilometer resolutions. This is a very advanced model called FESM, currently FESM 2, that is capable of deploying resolution where it's most needed. So we can have variable resolution on the planet, both for the ocean part and for the cryosphere. And this model is coupled to the IFS atmosphere and is used in both the project called NextGEMS and another project called ERI in Europe. Can I have the next slide? So just to say, there are groups worldwide aiming to develop coupled models in this range. A lot of testing has happened. So we had a couple of years back a milestone simulation from the German group at Max Planck running the so-called Apollo simulation down to 1 kilometer and showing us a really very exciting, fairly long weather forecast, reforecasting the day that the blue marble picture of the Earth was taken from the Apollo astronauts. And just to say that the science use cases are just about what happens to the details of distribution of precipitation, temperature, and all that, but also on what the small scales do on the general circulation. So what do all these ocean ideas and these boundary currents do for transport in the ocean, for instance? And also all the aspects of coupling between different components. And when we bring it all together, what does it mean for things like teleconnections and how the climate evolves? Could I have the next slide? I have a plot here of something I've been working on. So this is more for ERI. So in ERI, we are aiming multi-century simulations at about 10 kilometers, both in the atmosphere and the ocean. It's just to show that as we target hurricane intensity and we go from the typical CMIP resolution of over 100 kilometers down to about 10 kilometers, the so-called wind pressure relationship is much, much better simulated in these models. And we do have quite a few storms that, at least from the point of view of pressure, we can go category 5. From wind, we're a little bit short still, but this is 10 kilometers. This is not sub 10 kilometer. We have another paper with Alex Baker that targets a sub 10 kilometer and shows an even better relationship. And the caveat is these simulations were preparatory, so we don't yet have an ocean. And next slide. So based on Diamond, which was run in the last few years, we had a Diamond winter and a Diamond summer. A number of global groups started to work together. And so we had initially 40-day simulations, and we looked at the famous Turing test for climate that Tim Palmer had proposed. And we looked again at distribution of precipitation, and we looked at tropical cyclones and all that. There is now an opportunity to run one of these protocols for a whole year. And next slide. So the protocol comes from this paper by Daisuke Takasuka that was published last year, and we showed this plot before. We already said that there is no WITCZ in these simulations, but also we looked at things like the annual cycle of jets and how this is reproduced in such a model. And we have in the paper a number of suggestions on other things that we could look at in just 1 year simulation, things that can tell us about how correctly we reproduce key processes and process interactions. And there's a lot to be learned if we all work together like we did in diving 1 and 2 by running simulations like this for a whole year. I think now it's up to you, Andrew.
Yep. So one last slide on current work or emerging work is beyond Diamond. There's actually new work on trying to use these models to actually go into the details of doing process studies and looking at comparisons to satellites. So the Japanese group has been taking a lead with a new satellite, EarthCare, that was launched last year. EarthCare has a Doppler radar and HSRL, high spectral resolution LiDAR. So active sensors in space. It's pretty unprecedented resolution, and Doppler radar gives you not just reflectivity, it gives you velocities of hydrometeors in clouds. So this is a map of global precipitation, and this is a swath from the EarthCare satellite. And they've done 2 runs of their Earth system model, NICM, which is what we just saw from Takasuka. This is 3.5 kilometers, which is similar to what the Takasuka paper. This is actually running at 870 meters, so sub 1 kilometer, more like the Apollo simulations that Pierluigi showed. And you can see you actually get a good representation of what's happening, and there's some very interesting quantitative comparisons. And this is actually the precipitation comparison globally for that snapshot. So this is from Wusabro, and thanks to Masaki Sato at the University of Tokyo. So that's sort of these emerging things of where they're going on the global side. There's also a lot of regional kilometer scale modeling. These are mesoscale models, so they're typically weather models with boundary conditions. They're also regionally refined Earth system models, or they can even be global kilometer scale models. So there's sort of 2 ways to do this. And what's interesting here is sort of we're looking at the same event with 2 different approaches. This is a traditional approach using a mesoscale model, WRF, on the bottom. So the bottom left, where this is replaying a simulation of a flood in California, and doing it again with increasing temperature in the boundary conditions. So the same meteorology, but just changing the boundary conditions and running it forward. And then you get more and more precipitation you can see from this particular atmospheric river event. And then this is looking at a similar event for California, but with a regionally refined Earth system model from 14 kilometers down to 3.5 kilometers. And you see the distribution of precipitation intensity changing and sort of representing the topography in the Western United States. This has also been done in Europe. There's also, like Diamond, there's sort of ensembles of regional kilometer scale models. This has been the Cordex regional climate modeling group, which has been does simulations all over the planet and helps govern intercomparisons for different regions, has a framework pilot study on the Alps, for example, where you can see that resolution is needed in regions with significant topography. And so this is 3 kilometer resolution driven by sort of 15 kilometer resolution boundary conditions. And this is an example of a 2003 heat wave, where you see actually these are the observations in the upper left, the top row is 2 sets of observations, and the bottom row shows the high resolution and the low resolution ensemble, where you can actually resolve the different temperatures and the big temperature gradients in the valleys and in the peaks in this example. They can also, this is another example from the same experiment where you can look at precipitation, just showing both the mean, the frequency, intensity, and the heavy precipitation, so the 99th percentile. And you see how the 3 kilometer is actually doing much better at representing the patterns of the 99th percentile precipitation than the 12 kilometers in this region. So again, these are sort of different approaches. Here's one last one. The top is a reanalysis boundary conditions. This is called the CONUS 404 experiment. It's a regional climate model on the upper left, and this is run for the entire United States. This shows annual precipitation compared to gridded observations. And then this is a regionally refined model, free running. The bottom left here is the regionally refined model run for a couple winters in California. And then there's 2 different sets of observations, and then a similar simulation, the regional climate model, to what's shown in the upper panel with WRF run at 4 kilometers. So again, looking at the same event in different ways, but showing that particularly for things like orographic precipitation, this is sort of necessary to get that correct. So what's interesting is there's kind of some common issues in focus here. The regionally refined and global models, they deal with topographic and orographic precipitation, the placement of that with atmospheric rivers, convective organization, MCSs and IDCs, and then looking at their core sizes, the diurnal cycle precipitation, tropical cycle development, intensification, coupling of the surface, soil moisture, atmosphere, land interactions, and stream flow and runoff. So let's see, I guess I was going to keep going for a little bit on these, right? Yes. Yes, and I was going to pass it off. So what's interesting also is the parameterizations in kilometer scale, both regional climate models and global climate models are similar. We're using very similar methods for microphysics, radiation, deep convection, whether there is a deep convection scheme or not. And they often have different heritage for their turbulence and their planetary boundary layer, which is interesting. And just that's because one has been focused on the global models tend to focus on the larger scale motions over the ocean, while the mesoscale models, which are designed for weather and usually focused over land, often have parameterizations that are more designed for a land-based environment. Again, so common challenges in developing these models, whether you're doing regional or global, what is subgrid and what's explicit? When you're doing horizontal resolutions from 1 to 10 kilometers, you're in a sort of convective gray zone especially for deep convective motions. There are different ways to handle that. Also coupling across the components at kilometer scale, land and ocean in particular, or to ice, and also coupling all that to the atmosphere. And then the non-atmospheric components at kilometer scale, particularly the land surface and coastal, are a big issue. We're not talking too much about the land surface right now, but there's a lot of active development of kilometer scale land surface models, and the hydrology fundamentally changes when you get to kilometer scale, because as opposed to sort of 100-kilometer climate scale, because you start to have lateral transport, particularly in the subsurface. And then ocean spin up for longer circulation simulations is a real issue because it's hard to run these things for a long time. The computation, obviously global kilometer scale is exascale, and even the regional kilometer scale, the output can be exascale. So there are trade-offs between resolution, area, and ensemble sizes just in the computation. And what's even more important perhaps is data volumes and access. And that's sort of what we're getting to with the hackathon, that sharing these data sets is difficult. It's hard to move across platform. Storing data may actually be more expensive than computation. And the workflows and analysis we've been using, most of our traditional workflows ranging from saving the data, moving the data around, to analyzing the data, they simply fail when we're dealing with data sets that have millions of columns on the planet. And we're dealing with high time frequency as well. So there are some emerging solutions to this, and that's what we're actually been exploring and trying to bring people together on. And that's what we're actually going to be hacking in May, which we'll get to, and which I'll actually show some examples of at the end. But for computation, a number of groups have been using GPUs for acceleration. This gives us much more memory and compute efficiency. There's more cores available on these GPUs, so we're able to more efficiently use them. A traditional climate model is very inefficient in actually using floating point operations on CPUs because we're very data intensive. And so the GPUs are much more efficient. This allows us to use new exascale computers that have large numbers of GPUs, or even use cloud computing systems. There's lots of new developments developing rapidly with artificial intelligence and machine learning emulation of models, or different pieces of models for ensembles and for downscaling. And then this regionally refined global kilometer scale allows us to do multiple methods. We can do boundary condition forced events. We can actually do free running. We also gain factors of 10 speed up when we're only looking at one part of the planet, although we lose some of the global questions that we're trying to answer. Many of the questions, like I showed for California and for Europe, are actually local. And then we need to push the analysis into computation. So for example, to look at features like organized convection or tropical cyclones, you don't want to write all the data in the first place. You just want to get the data out that you need. So if you want to just find the tropical cyclone, you just want to output that data and the statistics of it. You don't want to output the gridded fields to have to calculate it. With data storage and access, it's easier to provide data access in situ than to move it. We can't move these data sets. We want to write less of them. We save checkpoints and we rerun if you didn't save something the first time. And this model intercomparison project model may fail at kilometer scale. We can't just put everything in an archive and expect people to get out what they need. That's okay. When you get to kilometer scale, there's such a diversity of questions that we may not be able to save what people want. We may have to bring the computation and the users together in a different way. So that means a couple of things about workflows. We have to bring the analysis platform to the data. We can't move it. That's also become more easy with technology. We'll show some examples of how you can actually serve up data to people easier, even for data centers that you would traditionally think are actually pretty locked down. And we can develop new workflows and parallelized tools for regridding, reading, and displaying data. We'll show some examples. And there's some new hierarchical data formats, sorry, it's still early, using data at the appropriate space and time scale to do the analysis we need without wasting time working on bits that we don't actually need to work with. We also have unstructured grids, not lat-long, and for a lot of applications, we just need to learn to work natively on the grid and not do a lot of regridding and sort of get away from that. And that brings us to some ways to solve this problem, and that's this kilometer scale hackathon. I'll turn over to Pierluigi.
Thanks, Andrew. So really trying to get this idea of bringing people to the data and working together to find the processes and find what the processes do to the climate system. We had this idea to expand on the Diamond 3 protocol and allow people to look at the data. So you have a map here with a representation of our initial idea of global nodes. The idea was to run a hackathon at each one of these nodes concurrently and to work together and communicate together as we do it. So can I have the next slide? This is how we started. Now we've lost a few people, but we still have a decent representation of the globe and of the two hemispheres. So these are the current nodes. So we have a couple in Asia, we have one in Australia, we have a couple in Europe, and we have 3 in the US, and then 2 in South America. And the idea is to have centers that can host the data and also have some computational power. So an example is the centers that we have in the UK and in Germany, where people have in the past come together, around 80 to 100 people, and spent a week analyzing the data using a very large number of cores attached to the disks and also attached to some other forms of storage to do very detailed process investigations and work together on such things. So we want to scale it up to the globe. Can I have the next one? So the idea is to advance this kind of approach and this kind of capability into these kilometer scale opportunities, let's call them, using output from both global and regional models. And this is also an opportunity to further expand the concept of the regional to global alliance, so that we have experiments that are very much compatible, and we can look at different aspects. So with the regional models, we have a much more controlled environment. With the global models, we have perhaps a better representation of teleconnections. So the idea is to combine these different approaches and test a number of technologies at these different nodes, using the same, as much as possible, the same workflows and tools. So we spread around basic software library and some common tools, and we have common goals for the analysis. So the idea is that each node would host 1 or 2 of these global simulations, and we have a specific format and a specific way to do that Andrew will talk about a bit later. The idea is to also store other data that each country might have. Particularly, it could be very special observations for a very special process or chain of processes. And the idea is to provide an initial idea of what things people could do and how they could do them by providing Python notebooks. That would be the foundations for what people set out to do. And we have a number of topics that we have already identified and a number of solutions we have already identified. And yes, it's in practice to bring the analysis workflows to each node, and all of that expertise coming together for 1 week to each one of these nodes, and then all of them together. Can I have the next slide? So these are the initially suggested scientific topics which are suitable for these 1-year simulations at kilometer scale. So one important topic is convective organization, so traveling organized convection. Examples are tropical cyclones, mesoscale convective systems, but also atmospheric rivers. And then connected to those is to analyze extreme precipitation. And then we talked about before is land-atmosphere interactions. So also some interesting things start to happen when you have these bits of organized convection happening at the right time in the diurnal cycle, but also happening at the right place. and all the aspects of whether it rains on dry patches or it rains on wet patches and all that. And now that we mostly disabled convective parameterization, can we simulate that correctly? And then all the issues of the interaction of the flow with proper mountains that are represented in these types of simulations. So the interaction of the flow, precipitation, and evapotranspiration on complex terrain, and the distribution and behavior of vegetation in complex terrain. And then all the impacts of these small-scale features. So does it matter that the convection is properly represented in terms of intensity, timing, how it travels, lifetime, and all that, on things like ways that propagate globally and on the large-scale circulation. So looking at jets, monsoons, ITCZ, and aspects of blocking and all that. So these are the sort of upscale goals. And yeah, the idea is to share these 1-year simulations, or these Diamond 3 simulations. So the suggested grid spacing is less than 10 kilometers, and both, again, global and regional models are welcome. The core protocol is described in Takasuka et al. 2024. So mostly we focus on a single year, which is the year 2020, because it's quite a neutral year. And that is specified by using observed SSTs and CIs. The start of the simulation is early 2020, and then it carries out all the way to March of the next year, so end of February of next year, so to have a full annual cycle with a bit of spin up at the beginning. And then there is quite a detailed output request. So there are a number of 3D fields that are output every 6 hours and have 25 pressure levels. Then there are a larger number of 2D fields at 3 hourly, and then there are a very select group of 2D fields which are hourly and instantaneous that allow us to investigate a number of the processes I mentioned. So the expected size for this is about 5 terabytes, and we could go even higher if we decided to use a different zoom level. And Andrew will tell you about zoom levels in a second when he talks about workflow. So, but anyway, order of 10 terabytes is not too bad, and we can host more than one of these simulations at each one of the nodes, and it is possible for people to perform analysis, and Andrew will tell you how. Oh, and I forgot this slide where these are the intended models. So some of the US models. So we have E3SM, we have the GFTL model, we have Earthworks, and we have GEOS, and then we have from Europe ICON IFS, from Japan we have NICAM, and from our group here in UK, the joint NCARS and UK group, we have the unified model that was run by Lorenzo Tomasini a while ago at 5 kilometers. And I'll pass over to you, Andrew.
Okay. So I'm going to finish up by talking a little bit about some of these interesting workflows, and at the end I'll show some examples in the slide, and we'll show some examples of some notebooks that to actually show you that this is pretty easy to use for those of you who were used to working with Python. So when you get to kilometer scale output, when you have tens of millions of columns on unstructured grids, this requires new methods. So something like 3.5 kilometer resolution works out to on the order of 40 to 50 million columns, depending on how your grid is discretized, assuming it's an equal area grid. So one way, which has been pioneered in our community by the sort of Destination Earth project and the DKRZ in Germany, is using something called HEALPIX, hierarchical equal area isolatitude pixelization, and then storing the data in ZAR stores, which are collections of netcdf files that I'll describe for ease of access. So HEALPIX was originally developed for processing analysis of the cosmic microwave background data. So this was another community that was faced 20 years ago with the issue that they were coming up with satellites to measure the cosmic microwave background, but they were very quickly going to have 50 million pixel sky maps at 9 wavelengths. So you can see where this starts to look like our problem. And so they've been working on this for the last 20 years, and there are mature tools from this community, both in things like Python and more traditional in C++, to actually work with this output, to read it, and to process it. The next piece of this is something called ZAR, which is a layer on top of netcdf that allows netcdf files to be allows a data set to be broken into lots of netcdf files, and you break them essentially into chunks across dimensions, the same way you'd sort of break up the processing of a model into chunks on a large computer, but you have metadata that tells you exactly what files and data chunks are where. This speeds up read times because you only need to read the chunks that you're asking for. And it also allows built-in parallelism if you use it correctly, because the computing system can actually go get separate files and do the same operation on them. The storage costs are the same. The only difference is, instead of having a big netcdf file, you have a directory. So it's a directory with a ZAR suffix instead of saying a netcdf file suffix. And then all these things can be wrapped in catalogs. So individual ZAR stores by variables, by levels, by season can be wrapped into catalogs to facilitate seamless use. It also allows you to take multiple models that are sort of chunked in different ways and access them in the same way. You can also then network this on object stores. And I'll show some examples of how this can be done. And the whole point is to actually only make sure you can only get the data you need and only do the processing you need, and to do it as parallel as possible. Okay, so the bad news is you have to remap this to a sort of this particular grid, which is basically, it's hierarchical. So these pictures show that each of the grids, basically the next level up, the zoom level, it's called, breaks each point into 4 points, and then you keep going. But if you actually want to take larger scale averages, you can go back to the identically lower resolution grids. So there's a certain utility to doing that. So you have to remap to this and convert to ZAR files. I'll demonstrate a workflow for this. Going from something like 3 kilometers, which is like, in this case, is about 25 million columns equal area, to 6 kilometer HealPix, which is about 12 million columns. I've done that for 6 months of 6 hourly data. It takes a few minutes to process and about 100 gigabytes of memory. You only have to do it once. The hierarchical, the advantage is that the grid split each cell into 4, so you could do processing at the appropriate level. It doesn't add much storage cost to do all the hierarchical levels. It's about 20 to 30%. ZAR files are super fast for most operations, as I'll show, and there's built-in tools for working with this. They support X-array, standard compression, all sorts of other things. So what does this look like? Here's some quick eye candy. So using, again, 6 kilometer data, so there's 12 million columns in this image. This is a snapshot. This is actually from the SCREAM, the DOE or system model. It's running at 3.5 kilometers. It's gridded to 6 kilometers to read a 23 gigabyte archive and plot one time sample of that. Took 2.3 seconds because it knows exactly what files it needs just to get the single time sample, and just brings those pixels back to get the plot. On my laptop, I can do the same thing on my laptop. This took more like 20 seconds on a single processor on my laptop. Some other sample plots. Here's a regional map of a similar thing, but zoomed in. So this is actually only zoom level 8. So this is 25 kilometers over the Western United States. This is a Hovmuller plot. So it's the Northern Hemisphere subtropics from 2015 to 35 north at every longitude. This is hourly data for an entire month. So this is 1 month of data showing propagation of convective systems and some diurnal cycle over land, basically. And then here's a global time series for that month. This is all using the OLR field. You can see there's a diurnal cycle of global mean OLR, and it's over a month. And this is a time average zonal mean. Okay, so which one of these actually takes the longest? And the way to think about that to plot, it's which one uses the most data. And ironically, that's actually the plot that doesn't look the prettiest. That's actually this global time series, or this time average zonal mean. They require you to actually read all the data to get it. And you really don't want to do this at 4 kilometers. This is the power of your 6 kilometers. This is the power of HealPix. You can actually go back to a high level and just get the global time series of the zonal mean at much lower resolution. And it's much faster. You can also do regional and network data. So HealPix can do regional grids. You basically map it to the HealPix format, and you put zeros on the outer sphere. And when you throw it into a ZAR archive, you just use a standard compression, and it puts all the data in there. And then it says, give me 1 million zeros. And that compresses pretty quickly. So it doesn't add much to do that. This is surface wind speed from a 1 kilometer regional run of ICON on the HealPix grid for the subtropical Atlantic. And this, as I'll show you, took 20 seconds to actually download the data across the internet, across a continent, and then plot on a laptop. So it's very handy to be able to use. We don't intend to just have models in this hackathon. There's a series of observational data sets that we're going to pass out to each node for comparison. We're focused because we've got a lot of global data. We're focused on actually processing a lot of the satellite data and putting it in a similar sort of HealPix format that's appropriate. This includes things like some sea surface height, but it includes all the series data for radiation, the reanalysis from ERA 5, precipitation data sets, a few of them, and some other things in here. So what I actually wanted to do is show you, if I've got a few minutes, which I will, take about 5 minutes, and actually show you the environment that we're actually going to use. And what I've done is I've taken that sample file when I made those plots and put all the zoom levels, which is about 25 or 30 gigabytes worth of data, just put it on my laptop. And let's see, whoops, I will stop sharing this. Let's see, I'm gonna stop sharing that. And I'm actually going to share something else, which is this. Okay, so hopefully now looking at a Jupyter notebook, you can see that. And actually, let me just take a look at the Q&A.
Just confirming that we can see your notebook.
You can? Okay, great. So just to show you, for those of you used to looking at Jupyter stuff, this uses mostly standard things like just NumPy and Xarray, and then there's some HealPix specific modules. The first one is the standard HealPix library. The second two are actually pieces from the EasyGems project, or the EasyGems library, which is produced at the DKRZ, and then the intake and ZAR for catalogs and formatting. I'm taking the data locally. This is zoom level 10, which is 6 kilometers, and you'll notice the read of the ZAR file is simple. Xarray open data set, and then you use a HealPix plotting command. And in this case, in 25 seconds, you can get the plot I showed you before, which is a global plot. You can also do a regional plot at a single time sample. This is set to do Europe, for example. This is also at 10 kilometers, and this just takes milliseconds. It's almost instantaneous to use a smaller amount of data. If you want to do this time series, so this is the global mean time series, I backed this off to level 8, so that's something like on the order of more like 25 kilometers, and that still is taking almost a minute. So it takes a long time to actually go through all the data, but you should never actually do this, because if you go back to the zoom level 0, which is 12 points on the planet, you can get the same thing in almost no time at all. It's 160 milliseconds, a tenth of a second. So it's exactly the same plot. Basically, it's the same data that goes in there. It's already been pre-averaged. So that's the real power of the hierarchy, is to do things at the appropriate level. This one, again, working on the 25 kilometer data to look at all the data, takes about 20 seconds to take a zonal mean. And then if you go down to this Hovmuller plot, this took almost no time at all. Again, working with the 25 kilometer data to take a Hovmuller plot. Just to show you just the online test, this is how this plot, using some standard things, just this EasyGems library, this just loads it over the network. So you open the ZAR file with a URL. This is on an object store at the DKRZ. So this plot, it basically goes from North America to Germany to grab the data. It only grabs the data it needs. So it's asking for, essentially, it sets up the subplots, and then it gets the data for one time, and then goes and plots that. That takes 25 seconds, and then this is actually doing an average. So it's averaging over a period of a day to do that. So it smooths it out because you're losing the high frequency fluctuation. But it also takes about 30 seconds. And then this is a more traditional climate model run from Icon. Again, this is opening a catalog, and it's assigning the catalog. It's basically assigning it to a data set which has pieces of the catalog. But the real power of the catalog is you can query it. It actually contains 3 different simulations, or contains 3 different time resolutions of data. So 1 day, 3 hourly, and 30 minutes. And it contains 7 different zoom levels. And so you can actually then plot, for example, this is just plotting the mean of the global average temperature, the sort of diurnal cycle, or the diurnal cycle, and then this is using the 30-minute data. And so that's all working in network data that's not actually here. And the creation commands, I won't go into that right now. I can just show some examples, but actually creating the data set is really not that hard. This is loading how the data set was created for Scream. You load a file, you create a set of pre-calculated weights. This takes on the order of about 9 minutes to do once at 6 kilometers, and then you can save that off. And then it takes, you can use those weights to plot the data with HealPix, the EasyGems work. That takes a few seconds. This actually remaps the whole data set. It's not actually doing it yet because you haven't actually told it to compute it. But you can actually take and look at the remap file, and you can plot that as well. You add the coordinate system for HealPix. This is all that HealPix adds to the files. It just adds some simple attributes so that HealPix knows how to operate on it. And then you just write it. This is the write to ZAR command. It's a simple thing. So it actually only takes about 1 minute and 20 seconds and uses about 115 gigabytes of memory to write about 3 months of 6 months of a 6-hourly data set. So, and I think I will stop there sharing that. We'll do so that's just some examples that we're basically just using standard once you start looking at this, it's pretty much standard X-array. So as a summary, we're making great progress in a lot of the global and regional kilometer scale model development. This hackathon is designed to expand our ability to work with models and increase the user base. This exascale models with petascale data require new processing and analysis paradigms that we're in the process of developing and demonstrating. It's really a learning exercise for us all. So join us, and there's a link to a general site there. If you go to the QR code, that goes to one of the WCRP ESMO pages and if you go down to how to join, there's a link to all the individual nodes. Many of them have registration sites that are already up. Some of them have pre-registration sites, and some of them have just information. And thank you for your time. I think we'll stop there. Stop sharing.
Thank you so much, Andrew and Pierluigi. This was very valuable information. I appreciated the discussion of the challenges and what's going on, and also appreciated the examples. Very nice to see that going on. We're going to start taking the questions. Just a reminder to our audience, the way to answer questions is to type them on the Q&A box. We already have one, so we're going to start with that question. This question comes from Marianne Alessandra Alata, and they would like to know, would there be any problem to participate if I am from Peru? Would it be enough to contact someone from other countries?
The answer is yes. There's going to be a node in Brazil, and there's likely going to be a node in Argentina. Those are listed on the they should be listed on the website. There's some pre-registration, so I would say contact other people in South America, and they can likely help. And there's a limited amount of travel funding. If you talk to the nodes, we may be able to provide some travel funding to move people around, particularly for those in not underrepresented countries in the global South.
I've just written some of the details in the Q&A.
Okay, great.
And can I ask the more general question, I guess, for the advice for potential participants who aren't based in a near a country where there's a node happening? Is the advice still to investigate travel options and travel funding?
The advice is to investigate travel funding. Some of the nodes may be providing some satellites. That's in other words, some remote access. The goal is to get people hacking in the same room, but we recognize that's not possible for everybody. So on a node we're not dictating how this is going to work, and we're not centralizing it. It's a very grassroots process. So some of the nodes, like I know in the United States, we may actually provide some satellite on-site facilities at some of the major research centers, in addition to the nodes, the physical nodes. But we're encouraging people to travel, to meet people, and to network if they can. So it's primarily an in-person event, but individual nodes may be doing things slightly differently.
Perfect, thanks. Just a reminder again, if you've got questions, watching online, then please feel free to stick those in the Q&A and we'll get to them. Can I ask on the scientific side of things, you had your list of kind of target topics and questions. Do you want to just talk a bit further around the extent to which these year-long simulations will now give different insights to the work that's already been done, focused around the 40-day simulations from Diamond 1 and 2?
Yeah, so I think,
Luigi, I don't know if you want to
yeah,
lead
maybe I'll take this one. I think we've already seen from the paper published by Takasuka et al. That there are aspects of the response. So already in Diamond, we saw there was an initial response to the initial conditions, then a second phase of the simulations in which the models were more free to develop their own solution. And in many ways, this is the bit where we start to be very interested. But one of the questions was, well, how long can it go? And to what extent are the processes realistic? And can we see things happening, like more than one cycle of the MJO? Can we see things that have to do with the annual cycle? So there are plenty of examples about the annual cycle, but also the other things that I think are really interesting are these bits of evidence about the upscale effect of these processes. And so there are suggested examples of things that will happen in these global simulations that are much harder to see in regional models, which are forced at the boundaries. So these interactions, so like traveling waves across the planet and all that, will be very much limited, as well as transports, big transports between land and sea, the strength of the hydrological cycle, and all sorts of other things. But it's this idea of extending the simulations beyond this time period in which the initial conditions still matter. And for some of these aspects, things like soil moisture will have a memory that goes beyond those 40 days. So there's also this interesting question of what we can see in terms of soil moisture at these very extreme scales. We have examples from many process studies done with regional models, but what if we have a system that has to develop its own hydrological cycle and sustain it? What do these simulations look like in that context?
And maybe just as we last call for any further Q&A coming in, Andrew, I guess you're on the observation side of things. You showed the example of the NCAR model running at sub-kilometers and comparisons with EarthCare. I guess any thoughts you may have on what the observable resolutions may be and the extent to which we're going beyond that in some of these models, and so in a sense, what's the useful scale to do some of these model evaluations at?
I think the EarthCare data is about the 1 kilometer resolution. And I think the other thing that a lot of people have targeted is there's a lot of individual long-term station data where people have done, there's climatologies available of really high resolution measurements, basically from a single super site. There's some in Europe, there's some in the United States. They're all over the planet where people have 20 years of measurements for particular, literally, soundings and radars and things like that. When you're down to the 1 to 5 kilometer resolution, you can really start to actually represent those things and those climatologies pretty well with these models. So I think that's the advantage, that we have a lot of observations at this sort of kilometer scale, and we have to worry less about the sort of subgrid variability at this kilometer scale. We're also in a regime where we don't have to worry about some of the process complexities. So this model, NCAR, is not running with a parameterized diagnostic deep convective parameterization. So it's basically explicit convection at 870 meters, which is a lot more realistic. It probably works very well, particularly out over the ocean where the motions are not quite as large. So or as intense. So I think there's really, and you can see even here, so this is a simulation, I think it was actually initialized, I think, within 18 or 24 hours before these observations, and you can actually see a pretty good representation of the actual reflectivity from the satellite. It also, at the process level, as a process modeler, it allows us to really understand what's going on with the simulations. Why are you getting the right reflectivity? Why are you getting the right vertical velocities? Are we getting the clouds for the right reasons, which gives us more confidence as we back off and try to understand climate with this.
All right.
And I should say one last comment. We're not focused this beyond diamond comparison. There's a separate comparison, which is called ECHO for Earth Care Orchestra. Orchestra was a Earth Care validation field project in the tropical Atlantic. So if you're interested, actually I mean, I'm happy to forward people's interest, but also talk to Masaki Sato at the University of Tokyo. This is from him, and they're running a sort of comparison of short runs with these kilometer scale models, just a few days for particular times in the summer of 2024 when they had lots of observations and they were doing validations of the satellite. That's what this is from. That's a separate effort if people are interested.
Thanks, Andrew. It's wonderful to start to see these cross validations between the models and this very high resolution model and also observations. I have a quick question and then we'll wrap up. So if any participant already have their own data, their own model simulations, can they bring it to the hackathon, or will the hackathon focus on specific data sets?
Again, as Pierluigi said, no, bring your own data. Talk to the node that you're working with, and most of the nodes have large capacity if you can get the data to them to actually be able to share it. And if it's interesting enough, we can share it broadly. So don't do it 2 days before the hackathon, because there's gonna be a lot of stuff moving around. But again, we're not controlling this at a central level. We're mostly grassroots. So the individual nodes have a lot of autonomy. So as you connect with a node, if you're going to go to a node, talk to them about data sets. And if you want to do analysis, it's certainly possible to get your own data to those nodes. And then we can share it if we have enough lead time, basically.
Excellent. So you heard it. If you have your own data, talk to your node coordinators. And so with just a few minutes remaining, we want to thank our panel of speakers again. Thank you, Andrew. Thank you, Pierluigi, for this excellent presentation and for answering our questions. Many thanks to all of you online for your attendance and participation today.
And just a reminder that we'll be sharing the recording via the WCRP webpage, and hopefully this will be a really helpful resource to people catching up after today's event as we look forward to participating in the hackathon. We've dropped the link, I hope, to the hackathon pages in the chat box as well. So please encourage everyone to go away and have a look and have an explore and get registering to local nodes when that opportunity arrives. In terms of these WCRP Digital Earth webinar series, any feedback on today's event is very welcome and can be sent to either Rosie or myself. And we're also very happy to hear at any time from anybody who wishes to volunteer a seminar on any related topics, either from yourself individually or where there may be a group of contributions from a particular organization or that cuts across. And I've no doubt that we'll hear some outcomes through future seminars of the hackathon events and the collaborations that develop through those as well. In terms of next time, we're looking forward to a speaker from Chile in a next webinar with a date to be confirmed in March. And we'll be updating the webinar web pages with news of future events and details on those shortly. So look out for emails from WCRP inviting people to register.
And we'll also inform registered participants when the recording is available today, when the recording of today's event is available. So please feel free to share that widely with your colleagues and other people interested on kilometer scale modeling. Thank you to Maureen and the WCRP Secretariat for all their support. And thank you to all of you online for joining us. See you next time.